All right, let's dive right into one of the biggest little mysteries in all of science. It's a puzzle that's hidden deep inside the core of every single atom in the universe, and it's called the case of the missing mass.
Now, I want you to think about that for a second. It feels wrong, right? I mean, it goes against everything we know. If you put 2 pounds of something in a bag with another 2 pounds, the bag weighs 4 pounds. Simple. But what if it didn't?
Well, believe it or not, in the bizarre world of the atomic nucleus, this is exactly what happens every single time. This isn't some tricky riddle. It's a fundamental fact of how our universe is put together. So let's start our investigation.
Okay, so every good investigation starts with the evidence. We're going to look at a super common atom, and you'll see pretty quickly that the math just doesn't add up.
So check this out. We've got an oxygen-16 nucleus. That means it has 8 protons and 8 neutrons. Simple enough. And using what we call atomic mass units, which is just how we weigh things that are crazy small, we can add up the individual masses of all 16 of those particles. We expect to get a total of 16.12744. But when scientists actually measure the whole oxygen-16 nucleus altogether, it's lighter. It's noticeably lighter.
The difference is 0.13691 atomic mass units. And no, this isn't just a measurement error. This mass is genuinely gone. We call this the mass defect. So the big question is, where in the world did it go?
To find our missing mass, we have to go to the scene of the crime, the atomic nucleus itself. And let me just tell you, this is one of the most extreme, mind-bending environments you could possibly imagine. First, let's just get the scale of this place right. We tend to think of atoms as tiny, solid little balls, but they're not even close. If you could blow an atom up to the size of a huge classroom, the nucleus in the center would be smaller than a pinhead. The rest is just empty space. Seriously, to put a number on it, the radius of the whole atom is about 10,000 times bigger than the radius of its nucleus. But here's the crazy part. That tiny nucleus contains over 99.9% of the atom's total mass. So what happens when you cram all that mass into such a tiny space? You get a density that is just absurd. We're talking 230 quadrillion kilograms per cubic meter. It's so dense our brains can't really even process it, and it's basically the same for all nuclei.
And inside this unbelievably dense space, we have our 2 key players, our nucleons. First, there's the proton, which has a positive charge. And then there's the neutron, which has no charge at all. These are the building blocks that we added up earlier.
So, we've got the evidence of the missing mass, we've surveyed the scene of the crime, and now it's time for the master clue, the breakthrough that cracks this entire case wide open. And it comes, of course, from the one and only Albert Einstein.
We've all seen it, right? E equals mc squared. But what does it actually mean? Well, it's so much more than a formula. It's a statement about the very fabric of reality. It means energy and mass aren't 2 different things. They are fundamentally 2 sides of the same coin.
And here's the absolute key to our puzzle. You can trade one for the other. Mass can literally turn into pure energy, and energy can turn into mass. Mass isn't always conserved on its own. Energy isn't always conserved on its own, but the total amount of mass energy in the universe, that's a constant.
Okay, it's time for the final act. We are going to use Einstein's massive clue to connect all the dots and finally solve the case of our missing mass in that oxygen nucleus.
So that mass we were looking for, it didn't just disappear into thin air. When those 8 protons and 8 neutrons were pulled together to form that oxygen nucleus, a tiny little fraction of their total mass was converted directly into a huge amount of energy.
And we have a name for that energy. It's called binding energy. It's the energy that was released when the nucleus was first formed, and now it acts like a cosmic superglue, holding all those protons and neutrons together. It's also the exact amount of energy you'd need to pump back in if you ever wanted to break that nucleus apart again.
And we can calculate it exactly. For our oxygen-16 atom, that tiny bit of missing mass is equivalent to 127.5 mega-electron volts of binding energy. And that, my friends, is the solution to the case of the missing mass. It wasn't missing at all. It just changed form.
But, solving one mystery just opens the door to an even bigger one. What are the consequences of all this incredible power locked away inside the atom's core? I mean, if forming a nucleus releases energy, can we get that energy back out somehow?
Well, this whole idea gives us a kind of roadmap to nuclear energy, and it looks like this. It's called the binding energy curve. All it does is plot how stable different nuclei are. The higher up you are on the curve, the more stable you are, the more tightly bound your nucleus is. And the peak of that stability? Right around iron. So here's the secret. You can release enormous amounts of energy by taking elements from the ends of the curve and moving them towards that stable peak in the middle.
And this reveals two main paths to get there. On the far right side of the curve, you have these really heavy, kind of unstable nuclei, like uranium. If you split them apart into smaller, more stable pieces, you move up the curve and release energy. That's fission. And on the far left side, you have really light things like hydrogen. If you can slam them together and fuse them into something heavier, you also move up the curve and release energy. And that, of course, is fusion.
And the amount of energy we're talking about is just immense. A single fission of one uranium atom releases about 200 mega-electron volts. That is, literally, millions of times more energy than you get from a typical chemical reaction, like burning a piece of coal. It's a whole different scale of power.
And fusion, well, that's the process that powers our sun and every single star you see in the night sky. Deep in the core of the sun, the pressure is so intense that it forces hydrogen atoms to fuse together to make helium. And every single second, that process converts a little bit of mass into the light and heat that makes all life on Earth possible. It all comes back to that tiny bit of missing mass. Which really brings us to the final, tantalizing thought. We figured out how to harness fission in our nuclear power plants. But the ultimate challenge, the quest for truly clean, almost limitless energy, is to master fusion, to build a miniature star right here on Earth. The science is all there, but the engineering challenge is one of the greatest we've ever faced. And to think it all started with a simple, almost impossible-sounding question about a little bit of missing mass.